I'm from the company that constructs the metro lines in Athens. My name is Leoutsakos. I'm going to talk about what we do to reduce the energy consumption in the new metro line that we have designed and we have just entered for construction in Athens. Is a new metro line 4. The outline of the presentation, I will first give a very short presentation of this new metro line. Outline the energy saving and energy optimization concepts for the new metro line. And these are mostly the result of the upgraded capabilities of IT technology that in the last years it has attained exceedingly good performances. Most of our systems, there are about 55 electromechanical systems in that metro line, and they're all controlled by state-of-the-art computer-controlled automations and other control systems. Also, the use of new materials and products is another reason contributing to that concept of reducing the energy consumption. We continue to use classic energy-saving solutions applied on our systems. And finally, we introduce a new concept of condition-based maintenance on this new line, aiming at the end of the day to, in parallel, minimize the carbon footprint both during construction of the project and during operation of the project. So this new metro line is approximately 13 kilometers in length with 15 new stations. It is a driverless line. It will be serving approximately 220,000 passengers daily, and the budget, the initial budget at the moment, is 1.5 billion euros. A metro system is an excellent example of energy sustainability. Not only energy sustainability, but also environmental sustainability, cost sustainability, and social sustainability, as it reduces the city traffic loads, the consumption of energy. Let me just say here that a metro system, I mean, if you take the metro instead of taking your car, you consume about 1/15 of the energy that in comparison. And that reduces also the pollution emissions. In terms of CO2 production, taking the metro reduces the CO2 production compared to taking your car, by approximately 1/5. And this is because in Greece the power company still uses lots of fossil fuels to produce electricity. So you do save, let's say, 1/15. You do spend 1/15 of the energy if you take the metro, but it's only about 1/5 of the improvement in the CO2 production. At the same time, you're taking the metro reduces the car accidents, the noise levels, and in general, it's promoting the sustainable growth of the city and makes definitely worthwhile, the substantial capital cost of constructing a metro line, which is of the order of 100 million euros per kilometer. In this presentation, I will outline 12 different ways of saving energy on this new line. Many of them are new measures and new ways of saving energy based on the computer-controlled automations of all our systems and the new driverless trains. Instead of going through each one of the titles, I will skip that slide and go directly into the first slide. Now, typically, a metro consumes energy. It's a very heavy consumer of energy. All the systems, and mainly the trains that work and move the passengers from point A to point B, they consume energy. Energy comes from the power company, medium voltage at 20 kilovolts, and then typically this is transmitted. It is first transformed from the AC 20 kilovolts AC voltage to DC through first a transformer, then a rectifier, and then through circuit breakers it goes to the trains that absorb this power and move. Now, when a train brakes, instantly the motors are turned into generators, and they give back the energy that they have as kinetic energy. This goes in terms of electrical energy into the third rail, as it's called, it's the conductor rail, which is at 750 DC, and raises its voltage. So if there are other trains in the vicinity, then they pick up this voltage and they use it. Typically, in the operation of our trains, this regeneration, as it's called, is of the order of 15% of the energy that you consume to start with. So the regeneration, in any case, saves about 15% of the energy. If you have more trains on the line, suppose that you have, let's say, a train every 1.5 minutes, typically now it's every, let's say, 3 minutes, then that figure could go up to 20%, 30%. So this is more or less the limit, about 30% of the energy that you could regenerate. Now, the energy that does not get absorbed by the other trains, it is redirected into some resistors which are on board the trains that heat up to approximately 400 degrees C, and they consume this wasted, if I could call it, energy into heat. And this heat is going into the tunnels and into the stations. That's why the metro needs to have very powerful ventilation systems to remove this heat, otherwise it's going to be very, very hot. So you waste energy because there's nothing to do with it after a train is braking. You have to do something with it. A percentage is taken up by other trains, okay? The remaining becomes heat, and you don't want that. So for this new line, what we're doing is that we're taking back this energy through the same electrical path, if you like, from the third rail of the trains, the conductor rail of the trains. We send it back to our substations, then we pass it through an inverter, through another transformer, and then send it back to the power company. So this is a different layout, if you like, of a rectifier substation that takes energy to accelerate the trains, but when the trains decelerate, they don't anymore consume this as heat, but they send it back to the power company by making it as AC from DC, then stepping it up to 20 kilovolts and sending it back to the company. One thing that still needs to be resolved in this whole process is the legislative background, because we will be giving energy back to the power company. At the end of the day, we will having a meter on this side and another meter on this side, and we will be paying the difference, the price difference. This new scheme that has been applied in London in a pilot case, but this is a case on a full metro line, which will go soon under construction. Will save an extra amount of energy if the blue bars are the energy consumed without any regeneration. Then if you apply regeneration, then you save this amount of energy. And if you apply this, sending back the energy to the power company, then you have also an extra little difference which you save, but at the end of the day, for this whole line, this could be approximately 1 million euros per year. And what this graph is showing is that when you have many trains, in other words, this says train headway of 90 seconds, that means one train is 90 seconds away from the other one, then there are many trains on the line, and when one train breaks, there will be another train in the vicinity to take up this energy. However, when the trains are more far apart, then you really do get a substantial benefit, which could go up to 15% of the energy that you consume originally. And this is a fair amount of energy and also less CO2 on the atmosphere. Another way of saving energy on the metro, as this is a driverless line, is a very, very complex system. It's called a signaling system. Is what makes trains move safely. And this has equipment on the trains, in the tunnels, in the stations, and in the control center. And all these are, I would say, state-of-the-art systems that really try to squeeze every amount possible of energy out of the kinetic energy of the trains. And what is actually happening is the following. When the train is moving, suppose we have one train and another train moving on the line, then everything on this line, let me say, will be the transfer of information will be wireless. So the first train, as it moves, it gives out its position and its kinematic characteristics, the speed, the acceleration and everything, and mainly its position, and transfers this information to the system through the wireless system to the control center. Then the control center knows exactly where this train is. And then this information is passed on, once the central system checks that everything is in order, then this is passed on through, again, the wireless system to the second train. This is an example of two trains, and then the second train would know exactly what to do so that it can keep a safe distance from the first train. This process is happening about 5 to 10 times per second for every train on the line. So the amount of data that goes back and forth is quite substantial. Now, together with this information of position of the train that the other trains know, then the control center knows the position, the exact position of every train and its kinematic characteristics. And therefore, it can phase the trains in the whole line so that when one train breaks to stop at a station, then another train could accelerate to go away from that station or a nearby station. So this energy is utilized from train to train, and that can lead to a very, very substantial saving of energy, which is again of the order of 15%, which is again of the order of millions of euros per year for the operations company. Another way of saving energy is what we call the dynamic train headways modulation. What this means is that typically we have trains on the line, let's say every 3 minutes or 2 minutes or 1.5 minutes. However, with the new systems that will be available and online everywhere from the line connecting to the control center, we have an online counting of the passengers that enter the system in every station through the passenger gates, typical passenger gates that are in every station. So the control center knows the exact number of passengers at any point in time in the system. So that, together with images from cameras both in the stations and the trains, also having a database of events information, like there may be a concert or a football match or something, then the control center has the ability to modulate the headways of the trains. In other words, if there are too many passengers, it will send more trains to serve the passengers. But if there are less passengers, then it can space out the trains a little more. So it will save some train trips, and that reduces the energy considerably. As a train, typically, to move from one station to the other, consumes about 15 or 20 kilowatt hours of energy. And if you can save one trip, then you save this amount of energy. And this is quite useful from this point of view. And the target is to have trains that are full of passengers and not empty, so that, or let's say partly full, so that we carry more people and less metal, because if you move a train with not many passengers, you carry more metal. Another nice system that we will have on this line that will also have an impact on the energy is that every train is something which at the moment we have the basics already in place in the existing metro lines, and this is the same in most metro lines around the world, is that when a train stops at a station and the passengers enter the train, then when the doors close, every carriage of the train knows its exact weight. And this is required because it needs to level its level on the next station with the platform. I mean, if there are 200 passengers on a carriage, on a car, or let's say 20 passengers, then it will have a different height. So it uses that information to level the height with the platform. In this case, and on this line, this information will be conveyed to the next station instantly, so passengers would know which cars are heavily loaded, which cars are partly loaded, and which cars are not loaded. So they will direct themselves on the platform to enter the empty cars. That will save some time in people going in and out, apart from the comfort, the comfort level of the passengers themselves. And so this overall process, which starts from the train that stops in one station, it weighs itself for every car, this information is transferred to the next station. It is displayed over each door, because I've failed to mention that on this new line there will be platform screen doors opening together with the train doors on the platforms. In other words, the platforms will be closed areas. So the displays above the doors will indicate which doors will lead to empty cars or to semi-empty cars or to full cars. In any case, this will save some seconds, and many networks, heavily loaded networks like, let's say, Shanghai or London, might use this saving in time to put more trains in the line, because 2 or 3 seconds per station, times, let's say, 20 or 30 stations, it's 1 or 1.5 minutes, you can squeeze one more train in. But in our case, this in any case saves the idle time of trains, and indirectly it saves energy. Then we move something which is a little closer to the ASHRAE topics, which is ventilation. In this case, is tunnel ventilation. So the tunnel ventilation concept for this new line will be new, and it relates to the fact that we have this energy return mechanism, which I talked earlier on. So there will not be heat given out in the tunnels as it used to be. The amount of heat given out in the tunnels due to train braking would be much reduced. So the tunnel ventilation systems would not need to operate so much. So there's an additional saving of energy in this case. This is a typical layout of one station and another station connected by a tunnel. At the ends of every station there are ventilation shafts. Each one has 2 big fans, 2 times 80 cubic meters per second. And they usually, in this case, will not operate during normal conditions, because there will not be a lot of heat in the tunnels. If there is some heat in the tunnels, then one of the shafts will turn on one of the fans in, let's say, half speed. The other shaft will be left open, and there will be this movement of air from the open shaft to the exhaust shaft, let's say, and it will clear out the heat that has been left over by the trains. So this is another way of saving energy by having a more efficient tunnel ventilation scheme. Let me just note here that the tunnel ventilation is typically on a metro, 50% or 60% of the energy is taken for the movement of the trains. From the remaining amount, the 40 or 50% remaining amount, half of it is taken by the ventilation. So if we can reduce the energy spent by the ventilation, then that is a very, very significant reduction in the overall energy which is spent. Another clever scheme has to do with the construction of the line. When we try to construct the line, and this is a cross-section of the tunnel and the 2 stations, and we try to give it this shape, that means when a train is leaving a station, gravity is assisting it in accelerating. And when it is arriving at the next station, gravity is assisting in braking. So there you have an additional amount of energy saving, which is approximately 5 to 8%. The downside is that you have to construct a ventilation shaft in the middle that will be deeper, and you will also need to have pumping, because all the water that would seep in through the tunnels would gather itself at this point. So all this plus and minus at the end of the day has an optimum gradient which is of the order of 2.5% for the tunnels, and that has a break-even period for the cost, the additional cost, of approximately 10 to 12 years. So this is another scheme that we will try to save energy in this new line. Finally, in continuation, we will use extensive LED lighting and advanced lighting control techniques. There's thousands of lighting fixtures in a metro line. Lines 2 and 3, if I remember well, today they have about 55 or 60,000 lighting fixtures. So there's a lot of energy spent there. By turning all those lighting fixtures into LED, we will save a significant amount of energy, and we will also reduce very, very significant the maintenance cost. This is mainly because the maintenance in a metro system is done during the night hours, and that costs even more. That will increase the lifetime of the lighting fixtures, And then LED lighting also has other advantages because it will reduce the cabling for lighting, the circuit breakers, the switchboards, everything will become smaller, the UPS sizes, and the batteries for supporting all these lighting systems. Also because all of us have to live together with the architectural side of things and designing metro stations from an architectural point of view, LED lighting can greatly improve architectural lighting as well. Finally, having spent a lot of energy until today, we try to, in this new line, to engineer all our lighting circuits using special sensors and dimmers and other ways of trying to save more on the lighting energy if we don't need it. There's many systems, as I said, 55 approximately electromechanical and railway systems on that metro line, and they're controlled by 4 main control systems in the control centers and the stations. One is called BACS, Building Automation Control System, that controls the mechanical facilities like ventilation, HVAC, etc. The second one is called PRCS, has to do with controlling the power, all the power systems in the metro line. The ICMS is Integrated Communications Management System. This controls all the telecom systems. And the final one is the one that controls the movement of trains. All these systems, and I do not want to go into details now, have their own energy saving functions. And further from that, equipments on their own, like escalators, for example, or lifts or escalators and travelators, they will stop operating when there's no load on them, and there are many similar characteristics on other systems as well to try and save energy from wherever possible on this line. For the operations company, saving energy is millions of euros at the end of the day, and this is very, very important for them. It makes the difference between having a red or going in the black or in the red in their fiscal sheets at the end of the year. Another thing that we will try to do on this metro line for the first time is that we will change our maintenance philosophy in condition-based maintenance. What is condition-based maintenance? In the old years when something broke, people fixed it. Then they realized that I'd better go into preventive maintenance, which is once every 6 months, once every year, or wherever is needed. I need to maintain it, and that at the end of the day leads to a reduced cost. However, now that all the systems are computer controlled with thousands of sensors and information going back and forth to the control systems, we can assess the state or the status of a system, whether it's healthy or unhealthy, or it is approaching failure, simply by looking at the sensors. So this is what is called condition-based maintenance. By monitoring the sensors, we can organize our maintenance in an improved manner, and we expect this to reduce our maintenance activities and cost by at least 15%. It could go up to 35%. At the same time, this will optimize our spare parts management and definitely, of course, save energy, because doing maintenance has a significant energy consumption because of all the machinery that needs to work to do the maintenance. We will still keep continuing having systems that we already have, like the cosine correction with the so-called load compensation in power substations. That will improve the cosine factor for all our multitude of electrical loads and improve that to approximately 95%. That's going to give an additional 5 to 6% of energy improvement in the electrical base loads, like fans and HVAC units, lifts, escalators, pumps, lighting, etc. And all the motors that we will use in our project, except the trains is a different category of motor, but all the other motors used in fans, chillers, air handling units, heat pumps, escalators, lifts, whatever, they will have to comply to EU derivatives on efficient motors. Finally, all this, apart from the energy saving and the money saving, we expect it to minimize the carbon footprint And this starts from day one of the construction of the project, because we have been very careful in not over-designing the stations, although sometimes architects would like to have this tendency. We will not try to, we're doing everything we can not to oversize the civil works and the concrete structures. Typically, civil workers might say that, okay, this wall needs to be 1 meter thick. Okay, let's make it 1.2 meters thick so that we're safe for this and that reason. Through careful finite elements analysis, we try to do what is necessary and not over-design our structures. We will try to utilize materials manufactured at close distances. For example, a granite tile coming in from a quarry in, let's say, China, has a very large carbon footprint if you compare it to a marble tile, which is taken out in a quarry in, near Athens, for example. So this is another reason that we will be considering in the implementation of our civil works. The use of recyclable materials in station tunnels, trains and systems, for example, trains are over 95% recyclable. And also minimize the transportation activities during construction, like dumping of soils when we excavate millions of cubic meters to construct a metro line. We try to find quarries in the near vicinity of the project to take the excavation materials to those quarries, fill them up, and then plant trees on them, rather than take it and dump it somewhere far away. And during operation, all the previously mentioned, during this presentation, all these previously mentioned measures will be taken in effect to efficiently operate our systems and reduce the energy consumption, both for the systems, for the traction energy that has to do with the motion of the trains, which is important for the majority of the energy spent, but also for the systems that support the stations and the remaining of the operation. At the same time, related to the carbon footprint, we will try to maximize, we're doing everything we can to maximize the life of systems through the condition-based maintenance that I mentioned, and through the having the information from the various sensors, as I said, of each system, identifying its status and its health, and proceeding accordingly with respect to energy saving. So, concluding, on this new driverless metro line that we have designed and we have tendered, and we hope to sign a contract for building it within the coming year, with 15 new stations and 20 more trains. We have implemented the schemes that have to do with the movement of the trains for the consumption through clever signaling systems and highly automated, computer-automated signaling systems. Also by returning energy back to the city 20 kilovolts medium voltage grid of the power company. Then saving energy through schemes that relate to the passengers, like I mentioned with the headways of the trains and the loading of the trains. Then to the systems themselves of the line, like improving the tunnel ventilation schemes, the profile alignment of the line, LED lighting, power compensation, etc. And finally, we hope that all this will significantly reduce the carbon footprint both during construction and operation, which is very important not only for us and for the city, but for the planet in general. I thank you very much, and this concludes my presentation.
Thank you, Dr. Leoutsakos. Do we have any questions? Okay, then I would like to ask a question, please. Oh.
Maybe a detailed question. You showed the profile change to reduce the braking energy. What's the trade-off between that strategy and regenerative braking?
There are two independent mechanisms. The regenerative braking relates solely to the position of the trains. where they are on the line. I mean, if they're close together and one brakes and the other one accelerates, for example, if you have a station and they're, let's say, this is ideal, both trains on the platform, one on one track, one on the other track. So if they go together, I mean, I'm sorry, I didn't say that. One train is on the platform and the other one is coming. So as it's coming and it's braking, it's giving its energy to the system, to the power system of the trains. The idea is when this train starts braking, then this train starts accelerating. So the energy goes directly to the other train. That has nothing to do with the alignment, the profile alignment of the line. Regeneration has to do with the positioning of the trains. This has to do with the vertical alignment of the line. It's two independent mechanisms, each one of which has its own energy saving part.
So there's not less energy to be recovered by the train going up a slope to stop as opposed to doing it on the flat?
It will do so. In fact, when this train is approaching this station and it's braking, then clearly gravity will help it and it will regenerate less energy.
That was my question.
Okay. It will regenerate less energy. So in this respect, yes, there is an interface between the two mechanisms. But still, out of this energy, our job, if you like, is to make sure that another train will be in the vicinity to pick up the energy that this train will give out, although it will be reduced as compared if this was flat. Yeah, I cannot quantify though this effect and how one interacts with the other in terms of numbers.
Yeah, I would guess you came out ahead. I just seemed like they wouldn't be additive.
No, they would not be additive. In fact, if we add all the percentages that we saw in this presentation, it will come up to more than 100%. This is clearly not the case. But in terms of the traction power, which is the movement of the trains, it is very significant. Let's say, in fact, to consider that through this original system, we will save, let's say, a percentage of 25%, and then add another 15, let's say 25%. I'm referring to this because these are typical headways as we have them today. So if you save this energy and then you save this additional amount as well, it is quite substantial. I mean, this is probably 35 or 40% of the total energy that you consume in the first place. So this is quite important. So this is one mechanism. On top of that, there's another 15% through the mechanism of the signaling systems, which phase the trains one to the other. Clearly, these are not additive, and if you gain the maximum of one, then you're unlikely to gain the maximum on the other. I cannot quantify this with numbers. We have not done this exercise.
Yeah, thank you. Appreciate it.
Any other questions? Please take it.
Good morning, I'm Lieutenant Commander Tsurakis from Hellenic Fleet Headquarters. I would like to ask you about this SCADA and systems automation, which are extremely vulnerable to cyber attacks, and this is a fact. Have you taken into account this fact, and in what way, in order to assure passenger safety?
This is a question which is a very interesting question, and is one which is the center point of discussion of many metros at this point in time everywhere in the world. For this line, we have done quite a lot of work in trying to ensure that these main four systems that we mentioned are less vulnerable, let's say, to cyber attacks. There are many different ways that this is done, and for each and one of those systems, there are different measures taken. This is one part of cyber security, as we call it. There's another part which has to do with procedures, which for the first time we will implement in the operations company. And then also for the first time, we will make sure from the beginning that the software that goes into all these systems goes through cybersecurity filters, if you like. However, is a very big question, is whether these cybersecurity filters, which filters means additional servers in the system, additional checking of the flow of data and all that, this leads to an inevitable reduction of the availability of your system. Because if you have a system with 5 components and you add another one or another 2 components for ensuring cybersecurity, then immediately you may have more points that could fail, so your availability goes down. So it's a very big question. What is the optimum way to do this? Today, what we do today is something very, very simple. Purposely, we do not have any connections with the internet on our operational systems. And if someone wants to maintain a system through the internet, I mean, if a company wants to do maintenance on a system remotely, then we will go physically and connect the connection that will take the system to the web. And then when this is finished, then we will take it out again. However, as all these systems that I mentioned are now very complex, and they're all networks that give and take information from everywhere to everywhere, more or less, this is not so easy to do anymore. So you have to have cybersecurity filters at the central servers of each one of those systems, which is not one server for each one of them. Each one of these systems has a series of servers. And in our specifications, the specifications that we have given out for this project, we have prescribed in detail what would need to be done for each one of those systems in terms of adding equipment that will ensure cybersecurity. But this, well, we have actually diverted it to the next phase of the design when the contractor comes. We need to balance it, as I said, with the availability of the systems. So, okay, this is a very general answer that I gave you. I don't know if...
Yeah, we can't discuss it.
Okay.
We should, but
let me say a few examples. In international conferences that we've been to, in roundtables, when the coordinator says, okay, now for every table, one member will be the operations manager of the metro, the other one will be the maintenance manager, the third chair will be the terrorist, the fourth one will be the passenger, and so on. And when the question is asked to the terrorist, how would you do your job best? In other words, what would you do to do the maximum possible damage on the metro? All quote-unquote terrorists, I mean the people who resemble this position, say to hack into the cloud and do what is not allowed to be done. For example, drive 2 trains to collide one with the other. That's why especially signaling systems have their own built-in cybersecurity mechanisms, which are extremely difficult to break. For example, when data is transmitted from a train to the control center and back, this data is always scrambled with an algorithm which is different for every message which is sent. And this is generated in the central servers. So it is extremely difficult to break this. However, one could do something easier. It could bring a suitcase that will give, let's say, electronic dirt to the system, because one downside of the systems is that they are all wireless. So if you can have a nice suitcase with electronic dirt, if I could call it like this, to fast, yes, that's it. And so the system has, I believe, at least this system definitely has all the safety precautions. If it cannot operate as it knows it should, it will stop. This is a big discussion everywhere at this point in time.
Okay, thank you very much. We have exceeded our time, so please, if you have any more questions, use the break time for them. Thank you, Leoutsakos.
Okay.